Last lecture we talked about the details that go into what is called Green's theorem. We have to have a simply closed curve where it is oriented the right way and the region inside it is called D. Green's theorem says that if you have the vector field F given by Pi plus Qj, then the integral of f along the boundary, along the curve, is the same as integrating over the region the quantity partial qx minus partial py. Because this is a surprising equality, the type of questions and applications is often that one side is easier to calculate and we use it to find the other side. So if finding the line integral is difficult, we might find out that calculating the double integral is easier. For instance, if this happens to be constant or zero, as is the case with conservative vector fields. And this could happen the other way around. Some double integral is difficult to calculate. Instead, we calculate the line integral. The book exercises give plenty of chance for you to practice these, but I identified a few skills that goes into succeeding in such questions. First, you need to be able to have some sketch of the curve or region, because the curves are described by it's the rectangle with the vertices here, 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 and here. In these cases, you are being described or given the boundary, but you have to make it a curve, and that means you have to be able to parameterize. For example, they say the region inside the circle of radius 2 at the origin, you should immediately be able to tell that this one is a positively oriented curve which goes around this boundary. So you have to be familiar with these. Another thing is sometimes you look at something like x to the 2 dx minus y dy. You want to be able to understand what vector field is being considered here and what are the p's and q's. One way here would be just to compare here up, and you see that then p is x squared and then q is negative y. And I told you to remember which partial you want to take. Here you will take partial of this with respect to y because it's next to dx. And here you want to take partial with respect to x because dy is here. Actually, this ends up being 0, both partials. So it turns out this is in fact 0 on any closed curve. By the way, I never mentioned this notation. To emphasize that the curve we're integrating over is closed, they put this loop here, probably with the orientation to also make sure that it's positively oriented. But just the circle is enough, small circle. You may or may not use this notation in your work. I won't take any points off if you don't. And finally, you need the skill to compute double integrals, obviously, which has been the topic of most of the chapters thus far. Now we turn to a very concrete application of double integral and the Green's theorem, and that is just amazing. So what it says is, okay, let's look at the region D here with the boundary given as a curve positively oriented. Now let me calculate a very specific integral for you. So double integral of the function 1 dA over d is maybe actually by definition just the area of D. So depending on what you define area to be, this could be a theorem, a claim, or it could be the very definition of what area is for arbitrary shapes, because after all, area is only meaningful for perfect rectangles, because you break it up into little squares and you say how many of the unit square fits in it. But for arbitrary shapes, what is area to begin with is itself a question, and one way around it is to define it to be exactly this. Now, we want to fix P and Q so that partial Q partial X minus partial P partial Y becomes 1. So anytime you have this whole thing equal to constant 1, you will have area equal to that. So there are millions of vector fields where this quantity is equal to just 1. And amongst them, we can guess is, for instance, if, okay, let me write it here. There are infinitely many choices of P and Q with partial Q partial X minus partial P partial Y just being constant 1 at all points. Some examples that are relevant to us and we will work with is, okay, so let's take Q to be just X. So Q of X, Y be just X. So partial X will be 1. And then take P to be constant, or just the constant that we love, 0. And in that case, that means, so area of D will be double integral over D of this particular function f. So these P's and Q's, but then that means we're looking at integral over the boundary. So let me put boundary of D. P dx, so I'm using now Green's theorem. So, and then Green's theorem comes here and says this is integral over the boundary, over the curve, describing the boundary of P dx minus Q, plus Q dy. Okay, and that means this will be P is 0 and Q is X, so that will be X dy. So now we have a consequence of Green's theorem as elegant as it can get. So it says that to find the area inside this region, integrate the vector field given by 0 and X, right? Q is X. Yeah. If you integrate this F along the boundary, you get the area. Yeah, the amazing part, the impressive part about here is that you in the integral, in the line integral, you don't even look inside the region. You're only traveling along the boundary. So philosophically, it's saying someone who's walking just along the boundary could detect the volume the volume of the piece that they travel inside. Suppose this is kind of a big forest, and by gathering data only along this path, you can tell how much surface area is entrapped inside the path that you travel. I think book has some exercises or maybe projects going towards showing you this with some more concrete examples, and I think there is some device even that works based on this observation. Okay, but this was just one example. So how about this? So example 1 of fixing P and Q so that this holds is this. Another one would be, let's say we take now Q to be constant, Q just be 0, and P this times, because I want to take partial Y, so I can say P at xy is just Y. This will give me partial Y will be 1, but there will be a negative the common practice is to put this negative not on. I could say minus y, but the common practice is to leave it this way and say then, similar to above, area of D is minus of integrating over the boundary the vector field coming from 0, sorry, p is y and this is 0, and p dx, so y dx minus q dy, q is 0. So that will be, yep, that will be our second area formula, which is analogous to the above except for minus sign. So this will be integrating f dr, this particular f dr over the boundaries. The same is here true also. And this time the vector field f for us is p is x, q is 0. So f dr. And then there is a third one, which is more symmetric. So combine the two above. So we love symmetric formulas. So here it seems like there's discrimination. X doesn't get the differential, y gets it. By the way, remember that these were defined previously. We talked about what is definition of this thing. And so when we combine the two, so if you add the two things here, if you add these two formulas, you get twice the area is their summation. So area of D, twice of that is this much, so 1/2 of over the boundary of x dy minus y dx. So this is where it comes from. In other words, here we are integrating, so 1/2 f dr, where my function f here is p is x, sorry, p is negative y, and q is x, right? Because this is the negative y dx plus x dy. Yeah. So if you integrate this vector field along the boundary and divide by half, you get the area. Pictorially, this vector field is just rotation around the circles, because if you are at xy here, negative yx is a vector perpendicular to that and of same size. So at this point it is equal to that. And if you move around circles, you get just tangents to the circle. So here it would be pointing that way. I'm attempting to draw them of same size, but visuals are tricky. And then when you reach here, it will be pointing this way, and so on. So this is how this vector field f negative yx looks like. If you get closer to the origin, you get the same picture except the vectors are shorter. And at the origin, by necessity, if you want to have continuity, they shrink to 0. So we're looking at this vector field which rotates counterclockwise around the plane, and the theorem says that if you pick the interesting part is that there is no restriction about the curve containing the origin or being anywhere else. It says that if you have any closed curve, and if you look at the integral of this vector field around that curve, you get twice the area of the region that it bounds. In language of physics, you can say this is the work done by this vector field on an object that travels with c. Right. So 3 formulas for calculation of area. Let me, as I did with the greens example, let's try to put this theorem to the test. Let's challenge it. How on earth could that be the case? So, and this is not because we don't believe in math or something. This is the way we should learn math. By looking at examples and trying to challenge statements, we get to appreciate their depth, and we also know how it works. So challenge to area equal integral of x dy. By example of, so of course we know it finally will bear out, but a rectangle. So let me draw a rectangle. And I'm going to be, for now, contending myself to the case where my rectangle is one corner sits at the origin, and I have here up the way, all the way up here, and then here. And this goes to A, and this goes to B, and this is the region D. The correct parameterization will be, we go this way, of course. And now here, let's see. So claim, the bold claim is that if I integrate x dy, I must get the area of this rectangle, which is AB. And it is a bold claim. The reason for this is as follows. Let me identify these edges by letters, Greek letters. So 1, 2, or Roman, 3 and 4, the edges. So number the edges by I through 1 to 4. Clearly, is it really? So I want you to check this. Integral of x dy along I, not I, sorry, along 4 is 0. Along the fourth edge, which is along the y-axis, this is 0. Well, because x is just 0 the whole time. Integral along the edge 1 of this thing and integral along the third edge of my curve is again 0. This time, because dy is 0, there is no change in y. When you parameterize this, these edges, you multiply into y prime of t dt, right? This is how you calculate it. And this will be x evaluated at y of, sorry, at the curve RT times that. And t has some range. But then y prime will be 0. So 3 edges actually voluntarily move out of the calculation. So these red edges are 0. They won't contribute anything. We are left with then, if this Green's theorem is to hold, we must have Green's theorem is to hold, we must have that integral along the second edge, edge number 2 of x dy should be a times b. Let's see if this guy has the information a and b. Is the information a and b, is data a and b encoded in this edge? Well, we see that the x which appears here is a, it's at a location, and then dy, this edge travels from 0 to b, so that possibly could hold, but let's actually calculate. So to calculate, if you want to calculate the line integral, what do you do? To calculate, parameterize edge number 2 as t goes to, okay, I had a student ask me what this means, t goes to. This is just a way to define a function, but let me use the more familiar one for you, a and t. So a and t as t goes from 0 to b parameterizes the edge in the right orientation. You start at the bottom at A0 and you go to AB. Notice the roles of A and B are so different. A appears in the function, in the parameterization, and B appears in the range of possible t. So with this parameterization, integral x dy over edge number 2 will be, so x quantity at RT. For every value of t, the x quantity will be just A. And then I do y prime of t dt from 0 to b. But what is y prime? So r prime of t is 0 and 1, and the y prime equals 1. So this becomes integrate a from 0 to b. This is a constant value, so that becomes a times b, rather b minus 0, and that's ab. And that's happy or sad depending on if you were rooting for Green's theorem or not. So it's really interesting and fun if you play around with these things. What happens if we shift this whole rectangle to somewhere here? What if we shift things here? The area should be the same, right? But something seems a bit odd, because look at this x quantity. Although we have the same edges and basically same parameterization, because r prime will be the same, y prime will be the same in these calculations, but then x is a bit too much then. X has increased. How can the final result still be the same as AB? The answer is that, well, x here has increased, right, on this edge, but then it has increased here just as well, and the amount of difference remains the same, also increased. So if we have pushed this whole rectangle by, say, 10 meters, 10 units to the right, this has increased by 10 and this has increased by 10, so the difference ends up being equal. The same happens with y. So in this case, these edges will, this edge will not be 0 anymore. It will be a positive value, but it will cancel out some excess here to compensate. These edges will remain 0 integrals because dy is 0. So that was just an example of a rectangle. Now you can try to work with circles and very thin rectangles, something like that. Then volume area is pretty much 0. And you see here that, well, this and this are still 0. If you're on the y-axis, this is also 0. You'll end up only with this. So if this is very small value, you get that. So there's a lot of room for really investigation and having fun if you have any curiosity surviving in you for math. So, that is the story of Green's theorem, and I think my examples were concrete enough to count as explicit exercises. So please again continue with the book exercises, and we'll see you in next section.